Welcome everybody. Thank you so much for coming to listen to us talk. Am I controlling this? I am controlling this. Sorry. Okay, I think that's me. Yeah, okay, there we go. Sorry about that. Thanks again for coming. We're super excited to share some of our work that we've been working on for a few years now, which is trying to enhance tumor immunogenicity by inhibiting nonsense-mediated decay. So as Matt was mentioning, we're on the early side of this. So we're certainly in that seeding phase, and we're looking here today to talk to you all to try to get partners and advice. On our ways, we see this project as leaving academia and moving into the biotech space. And so if you see me throughout the day, please come and talk to me. We're happy to get advice, of course, money, but also advice and just ideas on where this research should go. So let's talk about the unmet medical need. We think that there's a need to improve the immunogenic neoantigen presentation in tumor cells. Cancer immunotherapy, everybody here has heard of it. It's been a huge success over the last 10 to 15 years. Fortunately, as Dr. Vakuleski said, only 20% of patients respond, 50% in some niche cancers. But at the end of the day, getting that immune response takes two things: a really strong potent neoantigen, a strong go signal, a strong gas pedal, and then also turning off those brakes. And so checkpoint immune therapy has been awesome at turning off the brakes. There's been a ton of research in the latter as well to find alternatives to that. In fact, you're gonna hear one in the next presentation. He gave me $20 to say that. And, but for our presentation, what we're really focusing on is that neoantigen presentation, because there's not been as much work or effort into that. So that's what we're hoping to do here, which is that top part of that yellow signal. And so we're doing that by inhibiting nonsense-mediated decay. So unfortunately, Matt wouldn't let me lock the doors and hold you here for a 3-hour seminar on this. As an academic, that was really where I wanted to be. But so in lieu of that, I will say that NMD, going back to graduate school or undergrad, is just an RNA surveillance pathway. And so what it does in a normal context is it takes RNAs that are either mutant or that the cell doesn't need, and it destroys them before they can be translated. I won't go into the specifics of how that happens, but basically it just senses leftover proteins on that transcript. But what is interesting, and what kind of gave us our first idea that this might be something to target, is this data here on the right, which is you could look at mutations in a tumor that are likely to escape NMD, so that NMD would ignore. And those patients that have mutations like that tend to respond to checkpoint immune therapy 3 times as often as those that don't. So this is sort of our first indication this might be of interest to look at. So how might that happen? So this is sort of our very quick mechanism slide. I promise we're getting towards the end of the science part, and we'll get to the interesting part. And so here at the top, you're looking at an RNA transcript. It has some, in a cancer cell, let's say it's got some sort of small deletion, so a single base pair, let's say a G deleted or what have you. That then shifts your frame for your translation, and that introduces a PTC or an early stop codon. If you have NMD active, those transcripts are intercepted, they get degraded, nothing ever ends up happening. But if you inhibit NMD, like I'm showing you here on the right, what ends up happening is you have that frame shift and those get translated. And so now you have this really novel sequence. That novel sequence then gets translated into a small amount of novel peptide sequence in the protein, which gets processed by the proteasome and eventually translated and put on the cell surface and interpreted by the immune system. And what's really nice about this is that these are super potent neoantigens. This isn't a single mutation, point mutation with a single amino acid. This is 9, 10, 11 amino acids that immune system has never seen. Similar to like a virus or a bacteria being presented. And so it tends to generate this really strong, robust response. And this isn't just me saying this, we have evidence to support this. And so this is what we were kind of going after with this project. So with this in mind, we decided to run a high throughput screen. In the interest of time, I'm not gonna show any data from it, but suffice to say, we let the science come to us. So we used CRISPR and in whole cells induced 2 mutations that caused 2 genes to undergo NMD, and then we monitored the level of mutant protein from those 2 genes, and then we threw small molecules on top of that. And what was interesting is that after all was said and done, the readout from that hit the same target over and over from all the hits, and that was this target here, which is SMG1. It's a kinase. It sits at an important part of the NMD pathway process, and as far as we know to date, there's no alternatives to it. So when you hit NMD, it's a key gatekeeper. It really strongly downregulates that NMD pathway. It really hits it hard. And so as a sanity check, we looked in the literature and we said, okay, well in the middle here, what happens if you look at patients that have cancers that have naturally lower SMG levels, either due to natural variation or due to mutations in the pathway? And what's interesting here is that you see that those patients do much better, 20% survive. And I want to point out that this isn't a bubble in the curve. These are true survivors, right? This is a tail effect. So these are patients that are living 10 years and beyond, have survived their cancer. simply, and all they have is just a lower SMG level. And so, among other things, of course. And so if you want to, this would be sort of a monotherapy approach, you could say, but what about with immunotherapy? And if you look at patients that have mutations in the SMG1 specifically, they respond, again, 3 times better to immunotherapy, similar to what I said a couple slides ago. So hopefully at this point, you kind of agree, this is a good target, it's a robust target, it's leading to really profound effects both in human cancers. And so now we really wanted to chase down those small molecules that we had decided. So we put a little makeup on them and changed them around and made them a little bit better. And what we ended up with was KVS1. So this is the first reported potent, bioavailable, and selective SMG1 and really NMD inhibitor, period. There have been other SMG1 and NMD inhibitors, but they haven't really worked in vivo for a variety of reasons, but ours does. And so to sort of prove that to you, I'm showing you this data here. We simply took 2 human cancers, put them into a mouse, gave those mouse our compound, and then did RNA sequencing. And what I'm showing you here on the right is, on the top in red is H358 human tumors, and on the bottom is LS180. And each of the genes here is a gene that has an insertion or deletion mutation that shifts us out of frame and is targeted by NMD. What you can see is, in general, we get 3 to 4-fold increase in these mutant-specific RNA transcript levels. And if you look at the right with the gray, those are regular SNPs. We wouldn't expect those to go up, and they don't. That's an important control because we're not just impacting translation or transcription machinery here. We're specifically targeting the NMD part of those changes. So that's great, but do these RNAs go to the cell surface? If we look at mass spec data, we can actually see those neoantigens being presented, these mutant neoantigens being presented on the cell surface. And so with that in mind, we said, okay, well, can we target them? Can the immune system really hit it hard? And so to answer that, we went back into mice. We used now mouse cancers and put them back into a mouse, waited a week, randomized them, and then treated them with our compound daily for about 2 weeks. And what you can see here in the middle are 2 tumors, LLC and a BLAC6 background strain, and on the right, Ranca, which is a renal cancer, and a BALB/c background strain. And in both cases, in immune-competent mice, we see a significant tumor growth slowing when treated with our compound. And again, this is monotherapy. This is not in combination with anything else. And then on the bottom is an important control. When you have an immune-deficient mouse, we don't see any effects. So this sort of helps saying that the effect we're seeing is immune-mediated. It's not intratumor. It's not some random kind of off-target kinase activity. Now, I want to pause, though, and say right now that KVS1 is a really great early lead, but we don't think it's a final lead. And I think the data here is obvious, and everybody looking at it, we're not stopping the tumor. Tumor is still growing. But what I want to say is that we can get there. So if you take the same experiment and you knock out or knock down SMG1, you get this effect, which is total tumor stasis. And so for some reasons I'll show you in a minute, KVS1 doesn't have the greatest ADME PK information, but we think that we can get close. And again, we've got a great start compound here. So thinking about development in the future, so that we're early in our thinking here, but we're looking specifically at bladder and renal cancers. They look very attractive to us for potential clinical development, especially as a monotherapy. And so you can see here that on the right, you've got 3 subtypes of renal cancer and then bladder cancer. And on average, they have like 10 or so indels per tumor. So this is going to be lots of targets, right, for the immune system to be presented with each of these cancers. They also have significant patient populations, so recruitment should hopefully be easier. And finally, we have renal cancer cell model, like I showed you in the last slide, that's actually working. So again, we have preclinical models that are working for at least the renal side of things. So we're pretty excited about this as a potential path for development. So what are the advantages for our approach? Well, monotherapy is where we'd likely go for clinical development, just for ease. In the future, it'd probably be combined with immunotherapy. 230,000 patients in the US get that a year. And only 20% are going to respond. Simple math, that's 200,000 patients or so a year that would potentially be benefited by this therapy. Even a small entry into that market would be pretty large. The target and the pathway are unique in the space. We're ahead of everybody at this point. There's no other group that's farther along than we are for inhibiting either the pathway or this target. So we feel real confident with where we are, but want to move as quick as we can. We have IP covering the space, and then finally, we have a cryo-EM structure of a homolog of KVS1 in SMG1. So even though we do need to do a little bit more development, we think we can fast track that pretty quick. So what are we doing actively right now? We're working on the PK and ADME. And so this is the data I shared a minute ago. So KVS1 is 99% protein bound. We're not even getting to the in vitro IC50 in vivo with the data I showed you. So we feel like if we can improve some of this protein binding and working with medicinal chemists, we're actively doing that without losing specificity, which is really high for us right now. we're hoping to improve that and get to that tumor stasis that I showed you. And then second is obviously safety. This is a new target, but I've personally given this to over 1,000 mice at this point, and I've seen none of them are just falling over dead. There's no over toxicity, and we're just completing now a 28-day acute dose study where we're looking really seriously at this, and again, we haven't seen anything obvious that we're really concerned about. And so the team, it's led by myself and Dr. Kinsler here. Dr. Kathy Gabrielson's also, both of us are at Hopkins. Kathy's also at Hopkins, and she's been really instrumental with the safety work as a veterinary pathologist. And then also we work with Dr. Pauldahl and Dr. Vogelstein's. That picture they told me was taken a couple days ago. And then finally, so in summary, the unmet medical need, we think that there's some improvements that need to be made in helping tumors present these really potent, high quality, high quantity neoantigens. And we feel like disrupting SMG1 can get us there. And that KVS1 is a great early lead. And so again, I'd invite everybody here to, if you have any advice, we'd love to get it. And then obviously we're looking for partners to help us get there because this technology needs to come out of academics.
Thanks, Nick.